Good morning. So what you're going to see about over here, memory organization. So already I said you that we'll have often basic Harvard architecture. So in basic Harvard architecture, main advantage I said you already that we'll have two separate buses for program memory and data memory. So when we have two separate data buses, so what will happen? The content of program memory and the data memory, which can be accessed in parallel ways. So what is getting over here? So the number of clock cycles which is required for the memory access will get reduced over here. Okay. Whereas in case of an modifications proceed over here, so we'll have often input output program memory, so we'll have a data memory. So we can do several modifications or we can make several modifications in the case of an memory organization. Okay, and we'll have often address buses, data buses. So what are all these functions which is over here? Actually, all the things which carries the instruction store and they will have an immediate operand from the program memory. So they similarly they will have a carry the operations that are read from the data memory. So when I think over here, when I think of we will have a data buses. The data buses which carries the operands which are read from the data memory and they'll be carrying the data to be the written in the memory over here. Okay, and finally what we'll be saying of here, we'll have often it also carries the addresses which is needed for the instruction execution. So what about the registers? So what are all the registers which is used with often DSP process? We'll have often ALU, that is an auxiliary register, which consists of an 8 16-bit auxiliary registers, which is starting from AR0 to AR7, and we will have often 3-bit auxiliary register pointer, that is ARP, and we'll have often an unsigned 16-bit ALU. So whereas in the case of an auxiliary register ALU, which calculates indirect addresses by using inputs from auxiliary register, 16-bit index register, and then we'll have often auxiliary registers compare registers overall. Okay. What about the addressing mode? So addressing modes actually will have often parallel memory accesses instruction which must specify up to three memory. So we'll have often parallel memory instruction which is they have often three memory accesses. So what is the first thing? The thing is to be that actually the number of bits requirement is very large over on it. So we'll have often more memory, wider buses, and we'll have often more memory cycles. Okay. Whereas in case of how is the solution? So we'll have often register indirect addressing mode, so that we'll have often many addresses in one word instruction. So only a few bits are required over here. Since register bank is small and the parallel hardware to update the registers which containing the memory addresses over memory. So when you are seeing up here, so part of the functions of program controller actually will have often which decodes the instructions and then manages the CPU pipeline. It stores the status of CPU operation. It decodes the conditions of operations also. What are all the elements which is present in the program memory, program controller? So actually we'll have a 16-bit program counter, 16-bit status register, processes mode, status register, circular buffer control register, hardware stack, address generation logic register, instruction register, interrupt stack register, and interrupt map register. So when we're saying about an addressing mode, we have a short immediate addressing mode, short direct addressing mode, memory map addressing mode, circular buffer addressing mode, bit reverse addressing mode. Okay. So immediate addressing mode. So whenever we are given the data, so that has to be given with the immediate of what we are referring over here. Similarly, we are saying about an direct addressing mode. So directly, what are all the requirements which is given over here? Okay. If the address is to be that which has to be mapping with the memory. So when you are saying about a memory with the map, there is a memory map register. So when you are saying about here, we'll be having a fun circular buffer addressing mode. Okay, so circular buffer addressing modes, the thing is to be that we have to take over here to be the circular values over here, and finally we'll have a fun bit reverse addressing modes. Okay, the next thing actually we are in need to know what about an instruction level parallelism over here. What about the VLIW architectures? So each instruction specifies several operations which has to be done in parallel way. So the advantages when you are seeing up over here, so it has a simple hardware compilers which can start ILP easily. So whereas in the case of and disadvantages, we have a little compatibility between generations. So we don't have explicit NOPs block code size over there. So this is about an instruction level parallelisms and VLDO architecture. What about in the case of superscalar architectures, the hardware responsible for finding a ILP in a sequential program. So we'll have often advantage between generations. So we'll have often compatibility, whereas in the case of an disadvantage, actually we'll have often very complex hardware over there. Okay, what about explicitly parallel instruction computing? So it combines VLIW and superscalar architectures, whereas in the case of an instructions which are grouped into three operating blocks, and the templating block over the template block which tells hardware if instructions which can be executed in parallel and also gives information whether the block that can be executed in a parallel way. Whereas in the case of an barrel shifter, the barrel shifter which is used for scaling operations such as prescaling and input data, memory, operand, or the accumulated value before an ALU operation. So it has to perform a logical or arithmetic shift of accumulated value. So we'll have often post scaling the accumulated value before storing into a data memory. So what is multiplier adder unit? Multiplier adder unit which provides multiply and accumulate. So it has to do the multiplication at the same time it has to give off an accumulation value, which is capability in one pipeline state cycle. What will do the multiplier? The multiplier can perform signed as well as unsigned, even signed or an unsigned multiplication. So that is the thing what we'll be using over in the case of an multiplier and adder unit over on. Okay. So when you are saying up here, so what about the accumulators in geometry? Actually, they have two 40-bit accumulators. So what about they are on? They are to be used as an accumulator A and accumulator B over here. So each accumulator which is memory mapped. Okay, each accumulator is memory mapped, and they have partitioned into accumulators. That is, we have a lower, higher, and God bit. So we'll have often low word and then high word and then hard bit. So already I said you that we'll have often two 40-bit accumulators. So we'll have often A and B. For low word, we'll be using the notation AL, BL. For high word, we'll be using the notation AH, BH. For guard bit, so we'll be using often AG, BG. So lower bit stuff, when you're thinking about it, so we'll have some 0 to 16. Whereas higher order bit, we'll have some 16 to 31. Whereas guard bit, we'll have some 32 to 39. So this is the case which will be following up for the both of them, accumulator A and accumulator B. Okay, so this accumulator A and accumulator B, which can be configured as an destination register for mark unit or an ALU. The guard bit which is used as an head margin for computation. The only difference between accumulator A and B is that the bit 32 16 of A can be used as an input to multiplier of an mark unit over on it. Okay, so that is the thing when you are seeing up here in the case of an accumulator. Okay, so remaining thing we can see